Thank you, Nadav. Yeah, thanks for organizing this awesome inference seminar. And it's a great pleasure to come here and share our latest work. Today, I'm going to share Dynasor. So Dynasor stands for dynamic reasoner. We basically pick a few characters. Yeah. So efficiently serving reasoning programs with certain index. Okay. Um, and this is the work developed by students from my lab, like including Yichao Junda, Siqi, Zheyu, Andy, Auric, and myself. Okay, let's get started. So, I think everybody probably working in this area knows that reasoning models, right? Reasoning model has made a huge impact in the language model community recently. OpenAI released their O1 model last year in September, and O3 recently. Both models show strong ability for reasoning models to solve very, very complicated tasks. And this DeepSeek, right? It also was released by a Chinese firm, and this DeepSeek R1 in the last few weeks has made a huge impact in I would say, the entire industry. And it shows that the open source model can achieve great performance on reasoning. The success of these models lies in that they basically add a reasoning step, okay, between question and answer. So instead of directly answering the question after a user prompts the LLM, reasoning model will try to think for a while during this reasoning step before answering the question. Okay. So why is reasoning so important and why people care about them? So it turns out that if you put more tokens during inference time, so in this case, more output tokens at the reasoning step, right? The LLM will usually get to higher accuracy. So in short, the longer the inference is, the more attempts to answer a question. Therefore, it will translate it into more tokens spent in reasoning. And this will make your LLM achieve better results. Okay, very simple. So this is different from, I think in the previous year, people talk about scaling law. This is pretty different from the training time scaling law, which you aim for bigger model and more data in order to train a better model with higher accuracy. So test time compute simply tells you if the model thinks longer at inference time, they will just get higher accuracy. Okay. So to illustrate this so-called test time scaling, I just want to use this figure, which was originally posted by OpenAI when they released that O3 model. So the figure is the benchmarking results on a very, very challenging task, which is called ARC AGI. And you can see the figure in the bottom right. And I would like to look at this for a few seconds. And I think just by looking at this for a few seconds, you probably already know how to solve that, right? So this answer is pretty intuitive and simple to humans. So the solution simply just fill the closed area with a yellow color, okay? And this is very intuitive for human. But it turns out that at least before the reasoning model comes out, it's super difficult for LLMs, okay? Because this basically involves a little bit of reasoning. And back then, the accuracy of GPT-4o only achieves around 5%. And now with reasoning model, O1 mini achieves about 8%. And if you spend more compute budget, O1 will achieve basically 13% here. And if you spend even more, it will get to 32, okay? Depending how much effort you put into the reasoning process. And O3 is even stronger. So O3 low compute can achieve 76%, and O3 high compute almost breaks this benchmark again, okay? And this shows that the reasoning model do present great capability in solving problems as long as you give it more tokens at the reasoning and inference. Okay, but we also want to highlight that the cost. Okay, if you see the top right, that points basically shows O3 high. In order to achieve this accuracy, has to spend $3K at the inference to run this benchmark compared to say O3 low, which only use like $30. Okay, although with a lower accuracy. So the key ingredient here is that we spend more tokens at the inference time and way more tokens. Okay, like several orders of magnitude more to achieve a higher accuracy. This basically is essentially the test time scaling. Okay. So to summarize a little bit, instead of just naively throwing compute into LLM and let output tokens, we also have a so-called reasoning program, which is also essential to this test time scaling. Okay, these reasoning programs are essentially algorithms that help LLM to think the right way at inference time. Okay, so reasoning algorithms actually exist long before reasoning models come along. So and today I think the most popular reasoning program is the chain of thought. I think everybody in this area probably know this chain of thought. Okay, where we prompt the model to think step by step before getting to the answer, or more formally, given a user query queue, the model initiate a few steps of reasoning like this figure shows, and before finally giving the answer. And between these reasoning stages, this algorithm will basically have a few steps to refine the answer so far in order to get a better outcome. Okay, and today's reasoning models like DeepSeek R1 at least anecdotally O1 are trained to internalize chain of thought reasoning. So you already don't need to like explicitly prompt the model to enforce it to think step by step because they are already trained to do so. Okay. So there are also many other reasoning algorithms, but most of them are extension to chain of thought. Okay. For example, this self-consistency, a very famous trick for reasoning, is essentially launching a bunch of chain of thought and eventually do a majority voting to get the final answer. And this is a very famous algorithm, right? MCTS, which was used in AlphaGo to search for the optimal solution in Go. It is also a series of extension of chain of thought, okay, but with a different structure. So the combination of test time scaling law and the different forms of reasoning programs offer strong opportunity to make LLM even more intelligent, but at the cost of requiring much more compute, which makes inference multiple orders of magnitude more expensive than before. Okay, so one question is we want to ask in this talk is today's LLM inference system optimal at serving this kind of reasoning programs? Let's dive into this, okay? And I want to start illustrating this problem. So we identify a few problems in the current LLM inference system when serving LLM reasoning programs and reasoning algorithms and models. Okay, so what is this problem? The first problem is basically related to question difficulty. Okay, so suppose we have the four questions here: P1, P2, P3, P4. And if you just briefly take a look, you will know that the first question is super simple. The second question is relatively simple. The third question is pretty hard. Okay, in fact, it is a question from the latest benchmark called frontier math. And this frontier math is pretty hard in the sense that a math faculty can probably solve this in a few weeks. Okay, and the first problem is one of the 7 millionaire question in math, right? If you can solve it, you immediately get a 1 million award, right? Which is the most difficult. Okay. Now assume a user schedule these four requests together and send them to some reasoning models endpoint. Okay, and where you can decide if you want to use a low, mid, or high effort in inference. So we are just making a simplified assumption about these four queries. But you can imagine that an LLM service provider constantly basically receiving high volume of requests from diverse user and applications, and both them and the users basically want to solve this request with a low cost yet high accuracy, right? Because that's the serving goal. Okay. So in traditional LLM inference systems, inference time compute, or equivalently the number of generated tokens, is often evenly allocated to each request. And it is agnostic, the allocation is agnostic to the request difficulty. So a request terminates only when it meets like a very artificial stopping condition, for example, meeting a termination token or meeting a maximum sequence length, right? So that means assume P2 lies perfectly in the sweet spot of this uniform allocation. Here I basically say it's 8K tokens, okay? So basically, with this uniform allocation, this LLM endpoint will exactly use 8K tokens, and you will generate an answer for P2. Okay, after spending this 8K tokens, and you will also need to get charged for the 8K token worth money. And this is the optimal case. But now P1 comes, and it turns out that P1 is a super simple question. And ideally, you should spend much less token to attain the right answer. But because the system don't know about the question difficulty and it performs this kind of uniform allocation, it wastes much more tokens beyond what's needed. And this causes extra cost for this question, right? Because you don't have to spend 80 tokens here, okay, to get the answer. On the other hand, P3 also comes, okay, which is much harder. And it really needs more tokens to scale it to attain the right answer. But because the system is not aware of this, okay, it does not make the decision to scale to the desired point here. This leaves a gap where P3 didn't make to the correct answer, but still waste a lot of budget, right? And for P4, okay, the system also probably does not understand that this problem is so hard that it's impossible for the current model to solve. Ideally, it should return immediately when it realizes that the problem is too difficult. But in this situation, because of the uniform allocation scheme, it will keeps generating and until like it exhausted all the token budget, but it does not yield anything, no return. Okay. So with this illustration, you probably understand the problem now. So to attain the same accuracy, uniformly allocating computer resource to every request is apparently not optimal, it's very wasteful. The ideal case to allocate less, ideal case should be allocated less for easy ones and allocate more for difficult ones and almost none for impossible ones. And this achieves the same accuracy, but with less cost, okay? However, because the system is not aware of the question difficulty, it basically treats all the requests uniformly. It does not know how to allocate these resources, therefore wasting these resources. Okay, so to summarize the first problem, because the request difficulty varies and a uniform resource scaling rule will not ensure question getting to their ideal token allocation. And this makes easy question with too many budget and hard question doesn't get enough budget and the impossible questions cannot terminate early to save those tokens, okay? And all this is because the system is not aware of the question difficulty and it yields the resource allocation of a reasoning program to the users instead of taking control of it, okay? The second problem is that today's serving system actually do not know about the program, okay? So this means that the reasoning program structure is intrinsically unknown to the system. So for example, a user submitting a tree of thought program or MCTS tree, our current serving system will have no way understanding the relationship of each request, whether a node here is another node's parent or a child. And the lack of dependent information makes scheduling really hard, okay? Because in order to schedule them together, you have to know the dependent information. And the other more important problem is that the graph is actually not static. That means the system doesn't really know how much a program needs to expand across its lifetime. And if the expansion is serial or in parallel, and the system will not able to utilize this kind of opportunity. And the lack of expanding pattern also makes scheduling much harder than scheduling requests or scheduling a static graph. Okay, to summarize the second problem is about the program unaware scheduling. Because the system is unaware of the program structure, reasoning program structure, the system can only perform suboptimal scheduling. Okay, so let's do a recap of the problem. So there are two major challenges in efficiently serving reasoning programs. The first one is because the system is unaware of the question difficulty and therefore hard to make a decision for resource allocation and how to scale the problem with resources to basically meet their test time scaling law. And the second one is because the system is unaware of the reasoning program structure and therefore cannot make good decisions on scheduling the reasoning program. So essentially, both of the questions are inspiring us to find a proxy that can help us eventually dynamically allocate resources for different programs, whether it's based on difficulty, reasoning pattern, or something else. So the big question becomes, can we actually find some like a signal or metric that we can use this signal to design a system that can dynamically allocate inference-time resources for different questions, because that can basically achieve a kind of adaptive compute at inference time, right? And our answer is positive. We indeed find something that is really, really simple, lightweight, but effective. Okay, let's try to review how we achieve that. So as we discussed earlier, we face a challenge with difficulty unaware scanning for reasoning algorithms. So how can we address this challenge? So what if we could identify a proxy variable that is aware of difficulty and can help us control the scaling? The question is, does such a proxy variable naturally exist during the process of OM reasoning? Let's consider using basically certainty as our proxy variable. So certainty is a concept developed in machine learning community. It basically quantifies if the model or the algorithm, here the model is basically the LLM, right? If the LLM is certain about its own answer. And we have observed that the LLMs exhibit certain patterns in their confidence levels during reasoning. So intuitively, when faced with an easy problem, an LLM tends to be very certain about its answer. And conversely, when dealing with a difficult problem, it shows more uncertainty in its response. So let's look at a chain of thought example to understand this better. Okay. So let's examine how certainty can serve as a proxy for difficulty using chain of thought reasoning. So consider two problems. A simple one asking what's the answer of 2 plus 3? And a more complex one asking find the largest real part of this equation. Okay, this equation is pretty long. I'm not going to speak that, but you get me. Okay, so using a simple technique to extract answers during the reasoning process, we can see a clear pattern. So for this simple addition problem, the LLM constantly gives the answer 5 with high certainty. Okay. However, for the complex mathematical problem, the LLM shows uncertainty by frequently switching between different answers. Okay, and this answer is basically extracted during a long chain of thought. Okay, because you have some method to make sure that you extract the intermediate answers out of the chain of thought reasoning process. And this varying level of certainty naturally serves as an indicator of the difficulty. So in simple terms, so when a problem is easy for the LLM, it maintains high certainty in its answer. Okay, when a problem is difficult, this LLM will exhibit uncertainty. So now, how do we quantify the certainty in this kind of chain of thought reasoning? We basically use a 3-step pipeline. So first, we employ a simple technique to extract answers throughout the LLM's reasoning process. And second, we cluster these answers basically, we cluster these answers basically within a local sliding window. And this help us focus on the current source rather than the outdated ones. And third, we basically calculated this entropy based on this answer clustering. Okay, for example, we see 540 appearing with 1/2 of frequency, and both the two answers 303 and 435 they appear with 1/4 frequency each, and we can calculate an entropy of using this semantic entropy equation, and we can basically get that we can basically quantify so how certain the chain of thought reasoning process is about generating these answers. And remember here, higher entropy basically indicates lower certainty. Okay. Let's compare two scenarios. So on the left, we see the LLM sampling different answers during reasoning. This indicates lower certainty. Okay. And on the right, we see constant sampling of the same answer, which is 540. Okay, this should basically, if you substitute these values into the previous equation, you want to know this one has a different entropy value. It has a lower entropy value, which indicates a higher certainty. So this simple method of extracting answers and calculating entropy gives us basically a mathematical measure of the certainty. Okay, now let's address our next question. So is this certainty measurement applicable across different reasoning algorithms? So recall there are 3 types of most popular reasoning algorithms we discussed earlier, right? So chain of thought, where we generate and refine one thought at each reasoning step, and self-consistency, where the LLM samples multiple reasoning passes and aggregate several answers, and also a tree-based algorithm, MCTS, where the LLM searches along a tree using a progress reward model to score paths for node selection, and potentially generating multiple answers at each leaf node here. So we can basically obtain certainty measure for all 3 approaches. Okay, very simple. So for chain of thought, as we already discussed, we can just extract the intermediate answer at different at intermediate chain of thought step, and then we use a semantic entropy to calculate the certainty. So in self-consistency, it's the same, right? Because each self-consistency path will give you an answer, and you can basically cluster these answers, and you use the same equation I showed in my previous slides to calculate the certainty. And for tree-based algorithms, we have 2 options. We can use the process reward model. Its score as a certainty measure, since higher score indicate a better performance. Or alternatively, we can calculate the entropy from the answer at leaf nodes, which basically aligns with what we did with self-consistency and the chain of thought, right? We still use semantic entropy to basically serve as a proxy for certainty. Okay. To summarize, we have demonstrated that the certainty measurement can be effectively found and applied across various reasoning algorithms, right? And it's a very, very generic measure. So that's why our work is basically called a certainty index. Okay, so we name it certainty measurement as certainty index, and it's important to know that the certainty index is not the same. It's not the same as correctness. An LLM can be very certain about a wrong answer. Okay, and investing more compute power won't improve performance in such cases, right? Because I'm certain with the wrong answer, and no matter how much compute you invest, I will still be certainly wrong. Okay, and instead, certainty index basically tells us that whether additional compute investment will likely lead to a better performance, okay, but not a correct or incorrect performance. Okay, so a good certainty index should have three key properties. It should be simple, should be a very simple signal. It should be easy to extract, and it also should be accurately measure certainty. Okay. Now let's see how we can use this certainty index we discussed for resource allocation. So look at this figure from our QWQ model, which is a very famous inference like reasoning model released by the Chinese firm Alibaba. And we test this QWQ on the GSMAK dataset using long chain of thought. And we can observe some interesting patterns. So here, each blue point represents a solvable problem, okay, where the gray point here indicate a unsolvable problem. Okay, the way we get a solvable and unsolvable is basically we give it infinite compute. Okay, and we try to get the oracle. Okay, and the x-axis shows the ground truth compute needed, where the y-axis shows our certainty index. Okay, we measure the certainty index by calculating entropy at the point marked by this red line, basically at this step. Okay, this is that if we spend this compute, we can at this point we can try to extract all the answers and cluster them and estimate the certainty index. Okay, what we have discovered is very interesting. So certainty index strongly correlates with the amount of compute needed to reach a correct answer. So here, higher certainty index values generally indicate less compute is needed. Okay, and for implementing resource allocation based on certainty index, so we basically have two approaches. One is basically we just use this certainty index value as a simple threshold holding, okay, shown by this yellow line. Okay, we can stop allocating resources for points above this line since they have already reached their needed compute at the red line position. Okay, a more sophisticated approach using the green line, that is well, this is more complex to implement, and we call this green line the skyline, and it offers more fine-grained control on greater computing saving. Okay, so to summarize, this certainty index serves two crucial functions. One is it makes question difficulty measurable and transparent. Second is it essentially enables smart resource allocation. And this capability allows us to optimize our use of computing resources while maintaining the accuracy performance. Okay, and I think we spent a lot of time defining this certainty index, and now under this newly defined proxy variable certainty index, we basically developed our system Dynasor. And Dynasor is basically a system for adaptive resource allocation for solving reasoning algorithms. Okay, so Dynasor addresses three key challenges in reasoning algorithm solving, and let's explore this question one by one. So okay, so let's start with our first challenge. So how can we make the system aware of the reasoning program itself? Okay, we have implemented a straightforward reasoning program abstraction. Okay, and the programming interface is basically defined through define three important elements. The first one is how to calculate, how to scale the reasoning algorithm. That is how we can allocate more compute to it. The second is how to obtain certainty index for uncertainty measurement, which is this function. And the third element is basically how to aggregate the answers from multiple reasoning passes. Because if you remember, the way we estimate the certainty index is basically we try to extract all the intermediate answers and use that to calculate the semantic entropy. And our system requires both front-end and back-end components. So here this figure gives you a sense of the system architecture. So the application runtime handles local scheduling of reasoning programs and makes resource allocation decisions based on the statistical performance. And meanwhile, The system runtime basically manage the individual programs at the request level. And through this front-end and back-end engine and designs, we have achieved the program structure awareness in our system. Okay, this is basically address the first problem. And now let's basically examine how we allocate the resources based on certain index. Okay, this proxy variable we allocated. Okay, so let's look at a practical example using long chain of thought reasoning. So this application runtime continuously monitors certain index for each program during serving, and it makes dynamic resource allocation decisions based on this certain index measure based on its values. Okay, so the principle is straightforward. So then if a programmer programs with lower certain index should receive more resources because it means that the LLM is uncertain about the answer. So we should allocate more resources to it to basically make sure that you explore more, right? Well, those with higher certain index should receive less compute because that means that LLM's reasoning process is converging. It constantly generates many answers are the same, which are the same, right? No matter the answer is correct or incorrect, that means that the LLM is not making any new progress. So we basically should stop allocating more resources to this kind of program. Okay. And our final challenge is preventing interference between different reasoning programs. Okay. So to address this, we have implemented the server-side GAN scheduling. Let's compare two scenarios. So without this GAN scheduling, multiple reasoning programs with multiple requests each can degrade to round-robin scheduling, resulting in poor latency performance. And with GAN scheduling, we can prioritize requests within the same reasoning program. So remember, in a reasoning program, we can have a self-consistency, right? We can have a tree structure search and all. And during this kind of like a structured expansion, we actually create a lot of requests and we try to GAN schedule all of them together. And with this GAN scheduling, we can prioritize the requests within the same reasoning program structure, which will significantly improve the latency performance of the entire program. Okay. And we have also implemented several other scheduling improvements. And for comprehensive understanding of this enhancement, I encourage you to refer to our paper. So let's look at how Dynasor performs across like different scenarios, including offline inference and also online inference. So for batch processing, we compare Dynasor against two baselines. Okay, the first baseline is basically even resource allocation. The second baseline is basically a very intuitive baseline that is the generation length based allocation, which assumes that a simple problem will generate a shorter response. Okay, so basically we look at how many tokens it generates. Okay, to use that as an indicator for the question difficulty. And these results are pretty interesting and inspiring. So using rebased research on the GSMAK dataset, Dynasor achieves almost 50% of token saving with the same accuracy performance. And in online serving scenario, we benchmark Dynasor against SELAN and Parrot using even resource allocation. On the mass dataset using self-contained serving, we achieved up to 1.6 higher program rate. So basically, the system can support a higher arrival rate compared to baselines while still maintaining accuracy. Okay. We also tested our method on the state-of-the-art DeepSeek R1 long chain of thought reasoning model, which is basically the most popular reasoning model today in open source. And we focus on two of the most interesting challenging dataset, AIME and AMC. So AIME is basically the dataset that all the reasoning models trying to beat. Okay, it is a competition mathematical dataset. Okay, and AMC is another variant. Okay, and the results validate our approach. So compared to the baseline method that evenly allocated, which is this dotted line, okay, that evenly allocated tokens across programs, we achieve up to 24% of token saving while still maintaining exactly the same accuracy. That is, we can save almost 24% of tokens while without sacrificing accuracy using a certain index allocation. And these results basically demonstrate that Dynasor effectively optimizes resource allocation without a compromising performance. Okay, so to summarize a bit, I think I mainly covered two parts, right? Or maybe three parts. In the first part, I basically introduced the challenges of serving today's reasoning models, where existing systems do not actually know the question difficulty, and they also do not know the structure of these reasoning programs. And then in the second part, I started bringing a certain index as a proxy variable for measuring certainty for our reasoning. I also argue empirically that if you use this certain index as a measure, you can indeed use that as a proxy variable to tell the question difficulty and the needed compute to yield the correct answer for different questions with different difficulties. And based on this certain index variable, we build Dynasor for efficiently scaling LLM reasoning programs and with adaptive compute and GAN scheduling. Okay, that's pretty much all my talk, and it's a great work by my awesome students, and I'm happy to take questions.